our universe, our planet Earth, and even ourselves, everything is made up of the same components, of elementary particles. If we take a person and a chair and break them down into their components, we find atoms, and within them, electrons, quarks, and gluons. Without elementary particles, there would be no stable atoms. Everything would fall apart. They literally hold the world together. Elementary particles are not only the basic component of all matter, some can even penetrate any form of matter. Hamburg is home to DESY, the German electron synchrotron, one of the world's largest fundamental physics research centers. More than 2,000 scientists from over 40 countries work here. Particle physicist Christian Schwanenberger takes us into the enormous tunnel system below the DESY grounds. Schwanenberger is one of the world's most renowned particle physicists, a professor at the University of Hamburg and lead scientist at DESY. As only some parts of the tunnel are still being used for experiments, our team is allowed to film there.
We're going underground to the Hera accelerator. It's the largest accelerator that Germany has ever built.
Anyone entering the tunnel needs an oxygen unit for safety and has to report in by telephone.
Christian
Schwanenberger, hello. I'm entering the Hera tunnel at Hera West, going towards Hera North.
Behind the door is the heart of particle physics at DESY, the Hera tunnel. Hera stands for Hadron Electron Ring Accelerator.
Hera is so long that
you need a bike to get from one experiment to another. And you can see that it isn't actually a ring. We're riding through a straight section now. The electrons and protons are accelerated through these straight sections. The tunnel slowly starts to curve here. The particle beams aren't accelerated in this section, just redirected. The proton beam travels in the large upper vacuum tube, and the electron beam goes through the lower storage ring in the opposite direction. And if we were to travel much, much further, we'd eventually come out of the curve and see how this electron tube merges with the proton tube. The electrons are shot at the protons in the next detector.
The protons burst and release new elementary particles. What physics is aiming for with these particle collisions is the reconstruction of the beginning of space and time, the reconstruction of the Big Bang. Our universe emerged from a huge explosion some 13.8 billion years ago. Particle physics has not yet succeeded in pinpointing the actual moment. But it can look back to a millionth of a billionth of a second after the Big Bang. Debate about whether indivisible particles could exist goes back to the ancient Greeks some 2,500 years ago. The Greek philosopher Democritus, among others, called them atoms, from the ancient Greek atomos, meaning indivisible. The debate continued until 1911, when it was first experimentally proven that atoms themselves are indeed divisible. Atoms consist of electrons, neutrons, and protons. The term elementary particles first appeared in the 1930s. In the second half of the 20th century, teams from the US and DESY in Hamburg, among others, were finally able to demonstrate that protons and neutrons are also divisible and consist of quarks and gluons. The standard model of particle physics lists 4 groups of known elementary particles. The quark group consists of 6 particles in total. The leptons, including electrons and muons, also comprises 6 particles. The group of gauge bosons, the force particles, currently includes 4 types, including gluons and photons. Finally, there are the scalar bosons. So far, physics knows of only one elementary particle in this group, the Higgs boson. Detected in 2012, it is the most recent addition to the particle family. Berlin. At the Neues Museum, we meet Verena Lepper, the curator of Egyptian and Oriental papyri. She takes us to the papyrus collection. Some of the Oriental and ancient Egyptian manuscripts on display here were originally rolled up or folded, like these amulets. So far, they've had to be painstakingly unrolled and unfolded by hand.
The papyri are very fragile. When we want to open a piece, our papyrus conservator decides if it's possible, or if a package like this one, for example, will fall apart into 1,000 pieces. Of course, we don't want that.
Some 60,000 papyri and other manuscripts are stored in excavation boxes from 1907. Back then, huge quantities of such artifacts were found during excavations on the Elephantine Island in the Nile River. With conservator Sophie Elisabeth Breternitz, Verena Lepper is looking for papyri whose contents might be deciphered by means of particle physics without unfolding or damaging them. Using a handheld X-ray machine developed jointly with physicist Hans Eberhard Manka, they have found a papyrus packet that could have been printed with iron-containing ink, and have decided to scan the document with even more powerful X-rays. This is done at the Helmholtz Center for Materials and Energy in Berlin's Wannsee district. Tobias Alt specializes in tomographic imaging of a wide range of materials. For the papyrus packet from the Egyptian Museum, he draws on the pioneering research of a well-known German physicist. Wilhelm Conrad Röntgen discovered X-rays at the end of the 19th century. Shortly after, he succeeded in capturing the first images, revolutionizing medical diagnostics and earning him the Nobel Prize in Physics. For the first time, it was possible to visualize the bone structure of a living being without surgical intervention. The principle is relatively simple. X-rays are produced by the rapid acceleration of electrons, that is, elementary particles. The denser the material, the less radiation can penetrate it. Very dense material like bone appears white in the X-ray. Fluids and soft tissue like fat or muscle are less dense, and so appear gray. Organs containing large amounts of air like the lungs allow the majority of the rays through and appear black in the image. While X-rays can be harmful to living beings, they have long been a proven tool for non-destructive testing in materials research.
The X-rays pass through this fragment and then hit the detector. And we take a whole series of images, not just one. We rotate the sample once through 360 degrees and record a projection at very different angles. This way, we can generate a 3D reconstruction of the volume.
Sodass wir eine 3D-Rekonstruktion des Volumens errechnen können.
The scan only takes a few minutes and delivers numerous three-dimensional X-ray images of the papyrus packet. But the writing inside can still not be read. This is where scientists from the Zuse Institute in Berlin step in. Mathematician Daniel Baum and his team have developed software that can virtually unfold the papyrus packet. He traces the individual layers in the 3D model with the mouse. The computer program then virtually assembles the many X-ray images into a flat surface. The structure of the plant fibers is clearly visible. Finally, the image data from the X-ray image is transferred to the virtually unfolded papyrus, and distinct characters appear on the screen.
You can see the papyrus fibers really well.
Verena Lepper is versed in 15 Oriental scripts and languages from different eras, including Hieratic or Coptic, Aramaic, and Arabic.
For
the first time in the history of papyrus research, we can read a papyrus virtually without having to physically open it up. This is really sensational. This piece here is a Coptic text. Here is a P, which is the masculine article. Then this symbol, not Greek, but Coptic. This spells Pejoi and means, O Lord, Jesus Christ. This is the short form for Lord Jesus Christ in early Christianity, and a wonderful example of the fact that early Christianity and personal piety existed on elephantine, perhaps as early as the 4th century. Remember, this was a folded amulet that someone would have carried with them.
Thanks to physics and IT, some aspects of Christianity's early history can now be rewritten. Geneva. The European Organization for Nuclear Research, or CERN, is the world's largest research center in the field of particle physics. Here at the Swiss border with France, almost 20,000 scientists from all over the world have been researching the properties of elementary particles since 1954. We meet German particle physicist Christian Schwanenberger again at CERN. He is regularly in Switzerland to monitor experiments.
This is an overview of the Large Hadron Collider. We're here on the CERN site.
At the CERN's core is the Large Hadron Collider, the world's largest particle accelerator. The ring-shaped tunnel is almost 100 meters below ground.
Alles fängt eigentlich mit einer Flasche Wasserstoff an. Wasserstoff besteht aus
It all really starts with a bottle of hydrogen. Hydrogen consists of one proton and one electron. First, the electron is extracted and then the proton goes into a linear accelerator, where its energy is increased to half the speed of light. The proton is then fed through 3 more pre-accelerators before finally being directed into the Large Hadron Collider, where it's accelerated to near light speed.
Und dann auf Weltrekordenergie beschleunigt werden, also auf fast Lichtgeschwindigkeit.
In the collider, protons are accelerated in opposite directions and shot at each other at 4 points in the ring at almost the speed of light. 4 huge detectors measure the collisions.
One of these, called the CMS detector, is located directly opposite the CERN site, on the other side of the ring. That's where we're going now.
CMS stands for Compact Muon Solenoid, and it is one of the most exciting physics experiments of our time. Here in the CMS control room, the experiment's collisions are coordinated and monitored. Other physicists from all over the world are connected in real time, including a scientific team from DAISY in Hamburg.
Hallo Hamburg. Hallo.
Some 4,000 researchers from 55 countries worldwide are involved in the CMS experiment.
The CMS experiment is at the Large Hadron Collider, and it's an experiment to look at the fundamental building blocks of matter and understanding the fundamental forces in the universe and to learn more about how the universe was created. It's taking place at CERN because CERN has the most powerful accelerator in the world right now. And it's also a community that brings together institutes from all around the world and the expertise from them to really advance the field of particle physics.
In 2012, researchers at CERN achieved their greatest success to date: experimental proof of the long-sought Higgs boson. It was named after British physicist Peter Higgs, who, concurrently with his French colleague François Englert, described the properties of the as-yet unknown particle. The two were jointly awarded the Nobel Prize in Physics in 2013. Today is unusual. The proton collisions in the underground tunnel have been stopped in order to do maintenance work on the LHC or its detectors.
Das können wir vielleicht gerade mal zeigen.
This is a diagram of the CMS detector. Normally, the protons would be colliding in the center of the detector right now, but there aren't any protons in the collider at the moment. What we see instead are these particles here, which are called cosmic muons and are produced in cosmic rays. They pass linearly through the detector. So if the detector reconstructed something non-linear, then we would know that it was out of alignment and needed to be corrected. So we use these cosmic muons to calibrate our detectors very precisely.
Und dann wirklich die präziseste Physik herauszubekommen. Hey, how are you?
Because there are no particle collisions today, we are allowed into the 100-meter deep detector room.
When you are on the basement.
This would otherwise not be possible, as harmful radiation could be released during operation.
Hier ist jetzt der CMS-Detektor. Ja, das ist der schwerste Detektor in der Hochenergiephysik.
The CMS detector here is the heaviest detector in high-energy physics. It's 65% heavier than the Eiffel Tower. What we can't see is that the protons come from here and also from behind, and then they collide in the middle of the detector. When they collide, they practically explode, and then we analyze the fragments.
Und wir analysieren dann die Bruchstücke.
The proton collisions release new elementary particles like bosons, leptons, and quarks, which can then be measured in the CMS detector. By identifying the particles produced in each collision, measuring their momenta, trajectories, and energies, and then piecing together all the information, the scientists can recreate and describe what actually happens during the collision.
And in the end, this allows me to better study the microcosm of the particle. It's fascinating that the more you learn about its microcosm, the more you understand about the big picture, the origin of the universe. When two protons collide, for a fraction of a second, the collision recreates the conditions of the Big Bang. We can simulate these quarks and gluons swimming around in this cosmic soup by shooting protons at each other with incredibly high energy. It's like traveling back in time to the origins of our universe.
When the protons collide, the elementary particles that shoot off in all directions leave their traces in the individual segments of the detector. And these traces are translated into huge volumes of digital data. It all happens in this underground computer room, where all the data from the CMS detector is received.
Jetzt muss man sich vorstellen, im CMS-Detektor werden Pakete.
Imagine packets made up of 100 billion protons are shot at each other in the CMS detector. Not once, but 40 million packets per second. With each collision of these packets, some 60 protons collide with other protons, and the impacts release hundreds or thousands of particles. All these different particles are recorded by the detector. And in this room, all these physical signals from the collisions in the detector are then digitized. This flood of data is so huge that we have to pre-select and filter out the information we can't use. Otherwise, we can't store it all.
The pyramids of Giza, on the outskirts of the Egyptian capital Cairo, were built to stand for eternity, and are indeed the only remaining wonder of the ancient world. How many chambers are hidden inside the 3 pyramids is still a mystery. 3 main chambers, among others, have already been discovered, but researchers are certain there must be more. Perhaps even the body and burial artifacts of the pharaoh Cheops will be found. Since 2015, teams of researchers from Japan and France have been using particle physics to study the 3 pyramids of Giza. Using muon imaging, they are reconstructing their inner structure without damaging a single stone. In the standard model of particle physics, muons belong to the group of leptons. Muons are formed in the upper layers of the atmosphere when particles of cosmic radiation collide with air molecules. The particles, which travel at almost the speed of light, even penetrate large masses of stone. Around 10,000 muons hit every square meter of the Earth every minute at sea level. Scanners detect the muons that constantly race through the structure. Those that pass through many stone blocks lose a lot of energy and leave a relatively weak trace on the scanners. But if the muons flow through hollow space, they lose less energy, forming a stronger image on the scanners. In this way, they reveal the internal structure of the pyramids and help to discover previously hidden treasure chambers and other rooms without having to move a single stone. In 2017, the research teams made a spectacular discovery using muon imaging: a previously unknown 30-meter-long chamber in the Great Pyramid. Muon scanning has also proven its worth in inspecting the contaminated Fukushima nuclear reactor in Japan. Engineers can examine the condition and integrity of the power plant's outer shell from a greater distance, without having to physically enter the immediate, highly radioactive zone. Muon imaging is also used in volcanology, where the flow of elementary particles reveals the underground structure of volcanoes. This enables a kind of early warning system for potential volcanic eruptions. But the flow of elementary particles can not only illuminate matter, but also transmit information. Cellular phones are based on a discovery from the 19th century. They send and receive electromagnetic waves which, thanks to particle physics, we know are also elementary particles, namely photons. Cell phones operate using the electromagnetic force described in the standard model of particle physics. The silicon-based sensors in cell phones are based on the same principle as the detectors at CERN. Hamburg. The Bernhard Nocht Institute for Tropical Medicine, just north of the piers, is a research center where more than 400 scientists research dangerous pathogens. They study, for example, the exact blueprint of viruses using extremely high-intensity X-ray technology. Maria Rosenthal researches the structure of Bunya viruses, a group of dangerous pathogens introduced to Central Europe long ago by exotic insects. A Bunya infection, like the Lassa virus, can be fatal, and there are currently no vaccines or effective drugs. This is why the molecular structure of Bunya viruses needs to be completely decoded.
First, we have to generate the biological sample for examination. For example, we need protein crystals for X-ray analysis, because a single protein is not enough. The sample has to meet certain conditions for crystallization to be possible at all. We can easily see cells under a normal optical microscope, but we can't see proteins. For this, we need particle physics, which helps us to make even the smallest atomic units visible.
Atomare Einheiten sichtbar zu machen.
The cell cultures are swirled for 2 days at around 27 degrees to supply them with as much oxygen as possible. This is important for the production of the protein. Under the optical microscope, Maria Rosenthal checks whether the examples are suitable for further analysis. If a green shimmering signal forms in the cells, they have produced the desired protein. Before the sample can be examined in a particle accelerator, the proteins are sorted by size.
Diese Auftrennung der Proteine kann man hier jetzt ganz gut sehen.
We can see the separation of the proteins quite clearly here. This protein signal is shown in blue. It's a nice strong signal. And our target protein is in the peak here. So we can select the tubes where the target protein is well separated from all the others. That will be our pure sample, and we can continue working with it.
In the final step, the target protein from the cold room is mixed with various chemicals to grow protein crystals. This can take days or weeks.
Since proteins are not visible under an optical microscope, we need X-ray crystallography to see these proteins, these building blocks of viruses in the finest detail. These are the protein crystals that have formed. They vary in size and have very nice straight edges, which shows their high quality.
With a kind of miniature lasso, she fishes out the best crystals and stores them in a container filled with liquid nitrogen. Maria Rosenthal then takes them to DAISY, the German electron synchrotron in the west of Hamburg. This is also home to the Center for Structural Systems Biology, CSSB for short. Biology, chemistry, medicine, and physics research teams work together here in the field of infection biology. Right next to the CSSB building is a huge experiment hall. It is directly connected to a particle accelerator, the third generation of the positron electron tandem ring accelerator, Petra 3 for short. Petra 3 is a particle accelerator and one of the world's strongest X-ray generators. It allows researchers to examine the smallest samples, like the tiny crystals from the Bernhard Nocht Institute. The Mainz-based firm BioNTech has also used Petra 3 to investigate the effectiveness and messenger capability of RNA vaccines. Packets of electrons fly through the 2.3-kilometer particle accelerator ring at near light speed. Special magnets force them into a snaking path, causing them to emit high-intensity and highly focused X-rays. These X-rays are millions of times more intense than those from conventional sources, and up to 5,000 times finer than a human hair. The X-rays pass through some 50 measuring stations in several experiment halls, where the sample from the Bernhard Nocht Institute is now being further examined. Here, Maria Rosenthal meets structural biologist Christian Löw.
Hello, Maria.
Found my sample?
Yes, and I've even prepared it.
Super.
Christian Löw researches how the human body absorbs and transports nutrients and medications. He uses crystallography to study the structures of the molecules responsible for transport. This is how protein crystallography works. To be able to visualize the 3D structure of proteins with atomic-level precision, highly focused X-rays are beamed through the rotating cultivated crystal. The regularly arranged crystal structures deflect the X-rays and create a characteristic pattern on a detector. The protein's 3D structure can be determined from the position and intensity of the various light spots produced. Knowledge of the structure can now help in developing new drugs that target precisely where pathogens such as the Bunya virus are vulnerable. The samples from the Bernhard Nocht Institute have been measured, and the radiation collected in the detector has been converted into a 3D structural animation. Protein crystallography has greatly advanced and accelerated Maria Rosenthal and Christian Löw's research.
It's possible to develop a drug just by seeing whether it inhibits virus growth on cells. But it's very time-consuming, and you usually don't really understand why a drug works the way it does. In our case, using elementary particles, we can find out exactly how a drug works, or design a drug to stop certain mechanisms.
Developing such a drug is one of Christian Löw's missions. Atomically precise protein imaging helps him enormously because messenger proteins direct drugs to the parts of the body where the active ingredient is supposed to work.
The methods available here on campus, and Petra 3 in particular, made it possible to investigate these messenger systems in the first place. We work with tiny crystals, and only with the strong X-ray beam can we determine their structures. The development of these methods has been an absolute milestone for structural biology. And in the long term, it's essential to developing small molecules to combat specific proteins.
Crystallography's measuring accuracy is helping researchers to keep pace with the rapid spread of previously unresearched viruses.
So guys, how is the detector doing? Everything works fine?
Just a few hundred meters away at Daisy, we once again meet particle physicist Christian Schwanenberger. He and his team are analyzing the data from the particle collisions at CERN in Geneva, where proteins are again being collided.
Hallo Andi, grüß dich.
The Hamburg team is video linked to the control room of the CMS experiment. Schwanenberger's team in Germany now continuously checks the quality of the collision data from Switzerland.
Wir sehen jetzt hier Live-Bilder von der Datennahme am CMS-Experiment.
We're now seeing live images of the data collection of the CMS experiment. The protons collided here in the middle of the detector. And all these particles, fragments from the collision, have left a lot of traces in the detector, just like a jet leaves a trail of condensation in the sky. These are the green lines here. These red and blue dots represent the particles' measured energy.
In these precision analyses, data on known elementary particles is separated from what could possibly indicate new particles. And not only that.
Also man macht immer beides, man macht Präzisionsmessungen von Teilchen, die man
We do both.
Und wenn man da Abweichungen
We precisely measure the particles we know and try to learn from the deviations we find. But we also actively search for new particles that could help to explain things, like the fact that 85% of the universe is dark matter and only 15% is known matter, atoms and molecules. Like in this jar, I put black beans in for dark matter and white beans for known matter. Everything that's black is what we don't understand. That's dark matter. And that's what we're looking for. It's one of the biggest mysteries in science.
But also with telescopes in space. In the search for dark matter, there is even an experiment in which light is supposed to penetrate a solid wall. Axel Lindner heads the ALPS experiment, which is set up in a roughly 300-meter-long straight section of the Hera Tunnel at Daisy in Hamburg. ALPS stands for Any Light Particle Search. Lindner is a particle physicist at Daisy and devises novel particle physics experiments. A team of more than 200 specialists has developed and built the entire ALPS facility at Daisy over a period of 12 years. It is the first experiment worldwide in which very light particles of dark matter could be produced and detected in the laboratory. To do this, light would have to pass through an opaque wall, which is technically impossible.
We're trying to find something completely new, namely dark matter, and we're doing this by attempting things that shouldn't actually work, like this. We shine a flashlight on a wall, and normally nothing gets through. We use much more elaborate methods. And if a bit of light does get through the wall, then we can only explain it by the existence of a new form of matter, dark matter. So we're examining what we think is impossible to see if it's possible after all. If it is, we have found something completely new.
In the ALPS experiment, laser light will be amplified by a factor of 10,000 in a type of microchamber. The light will then pass through a strong magnetic field. In theory, a photon or light particle could be transformed into an axion, as the new elementary particle will be called if it can be detected. The laser light would be stopped by the wall, but the axion would simply pass through, because nothing can stop dark matter. In the magnetic field on the other side, the axion should be transformed back into a photon or light. A detector would measure the light particle that seems to have passed through the wall. Transformations, if they occur at all, would be extremely rare. The detector must therefore be able to recognize a few photons per day. If it succeeds, a new dark matter particle will have been found, which would be a sensational discovery.
For me, success is the fulfillment of a technological goal, so I'm very certain that our Alps experiments will succeed. Only nature can decide if we will find dark matter.
No one knows how long it will take to solve the mystery of dark matter. But the large number of particle physics experiments worldwide makes new discoveries more and more likely. With very tangible benefits.
If we look back, we see that what really holds our world together, electricity, electromagnetic waves, the internet, X-rays, came from completely far-fetched, groundbreaking research into completely new things.
As a particle physicist, it's sometimes hard to explain what you're actually doing. You can't hear the particles, you can't see them, you can't taste or smell them. But I still think it's important to research these elementary particles. Ultimately, it's the only way to understand where we've come from.
Physics is nothing more or less than applied or practical philosophy. We can explain the world. We know how to approach it. It's already working brilliantly. We apply precision cosmology and precision particle physics. Dark matter is still a missing piece, but then we'll have a complete picture of how we actually came into the world. And that is the fundamental question of philosophy.
The thing that's so fascinating about particle physics is that we can describe this complex matter, everything that surrounds us, in terms of elementary particles. And you almost think someone must have been clever enough to formulate our world, the world of elementary particles, relatively simply. Almost like it was planned.
irgendwie